right, so I wanted the chance to kind of walk through the test. I know you have access to the solution, but sometimes it's helpful to hear somebody talk through it. So if that's helpful to you, here you go. All right, so first question was asking, it was a conceptual question asking about point S on the TV diagram. So let's see, so point S is right here, and it's in that superheated region. And so it's asking if it has a quality of 1. So quality is the mass of your saturated vapor over your total mass, and it is only for the two-phase region. It's only if it's saturated. And so that means that it could be if it's under the dome or it's on the dome, that a quality would be defined. But if it's superheated or if it's compressed, then their quality is not defined. And so the answer would be false. Second question, a gas contained within a piston cylinder assembly undergoes so it's undergoes a couple of processes. So two processes. It's on a PV diagram. So from 1 to 2, you can see that the pressure doesn't change. So pressure is constant. And then from 2 to 3 here, you can see that the volume doesn't change. So the volume is constant. So it's a constant pressure process followed by a constant volume process. So it could be either one of these. And since the volume is increasing, it's an expansion process. So it's going to be this guy right here. It's going to be B. B. Sorry, make it look like it's B. All right, specific volume is the reciprocal of density. I think most people kind of got this guy. 1 over density, right? The units here, this would be, density would be kilograms per meters cubed. So this whole thing would be meters cubed over kilograms, which is exactly what specific volume is. Number 4, a closed system always contains the same matter. There's no transfer of matter across its boundary, and that's absolutely true. That's what a closed system is. A control volume, so this is an open system. Two different ways of saying the same thing. Kind of like a closed system, we can call that a control mass. So these terms are used interchangeably. Control volume is a special type of closed system that does not interact in any way with its surroundings. And that's not true. That's actually false. So if it doesn't interact with its surroundings in any way, that means there's no transfer of energy or mass or work. This is something that's called an isolated system, right? And it's a very special case, right? So there's no heat transfer, no work, no mass transferred across the system boundary. All right, so now we're on to problem 6. So we have 2 kilograms of water undergoes an isothermal process. So I'm going to go ahead and write what I know here. So I know that number 1, it's water, and I know I have 2 kilograms of it. And then I'm going to try to write as many properties that I know. So as far as, the intensive property list, remember temperature, pressure, specific volume, quality if it's applicable. And at this point in the semester, those were the properties that we were familiar with, those 4 things. So, all right, I've got the mass. I know it undergoes an isothermal process, 180 degrees, and isothermal means that the temperature doesn't change. It's initially at 7 bar, and then it goes to a volume of 0.7 meter cubed. Now that's related to specific volume, but it's not the same thing. So we're going to have to probably calculate the specific volume, which should be okay. So we need to find the initial volume. Let's put that initial volume V1. Oops, and I just wrote specific volume, didn't I? So V1 units are in meters cubed. Let's see, so I'll write it like this. If it's saturated, we want to find the final quality. If it is superheated, then I want to find the final pressure, and we'll put it in bar. Okay. Then I want to write things on a TV and a PV diagram. All right, there we go. So first things first, let's get our V1. Um, so I could see that I have temperature and pressure, and as long as my water is in a single phase, superheated or compressed, then that will be enough to fix my state. And I know that the volume is the mass times little volume. And again, if I'm able to fix my state, then I'm going to be able to get this specific volume here. All right, so 180 degrees, 7 bar. So the first thing that you want to do, go to your saturated tables to figure out what phase you're in. So 180, so I'm going to A2. I could have gone to A3, it doesn't really matter. Right? Because A3 is organized by pressure, but we'll go both ways to make sure. So 180 degrees, if it were going to be saturated, my pressure would have to be 10.02 bar, and I'm at 7 bar. So my pressure is less than PSAT, so I know that it's superheated. Okay, so I go to my superheated tables. I could have also looked in my table A3. So the saturated tables that are organized by pressure. So 7 bar, that's all the way here at the bottom. And I can see that if it were going to be saturated, then I would have to be, let me make sure, so we were at 180, is that right? Yeah. So my temperature, my T1, is greater than Tsat at P1. So again, I'm superheated. Both tables would tell me the same thing. So I'm going to go to my superheated tables, and I'm going to go, they're organized in boxes of pressure. All right, so these are A4 superheated water. Okay, and I'm looking at 7 bar and 180 degrees Celsius. Perfect. So I got 7 bar and 180. So I do need to kind of like zoop, look on over, and there's my specific volume. So 0.2847 is the number I'm going with. Okay. So this is going to be 2 kilograms times 0.2847 meters cubed per kilogram. So you can see that's going to give me things in terms of meters cubed. I've got 0.5694 meters cubed, and there's my V1. Right. And now we've got second part. So they're telling us if it's saturated, get this. If it's superheated, get this. So I do need to figure out, is it saturated or is it superheated? So I need two independent intensive properties. And remember the list I have: temperature, pressure, quality, or I'm sorry, specific volume, and if it's applicable quality. So I know temperature, and the other property that I could probably get a hold of at state 2 is going to be my specific volume. So let's go ahead and get that. So I know V1 is going to be the volume at state 2 over the mass, which doesn't change, right? Okay, so 0.7 meters cubed over 2 kilograms. Perfect. So that's going to be 0.35. And the units are going to be meters cubed per kilogram. All right. So now we have two independent intensive properties. I know T2, 180 degrees, and I know the specific volume. And I'm sorry, that should be 2. I know the specific volume V2, which is 0.35 meters cubed per kilogram. And so now I need to figure out what phase we're in. So I go to, again, my saturated tables, and I'm going to go to the ones that are organized by temperature, right? Because I have the temperature. So let's go to table A2. There we go. All right. So I can see at 180 degrees, right? Remember T2, 180 degrees. V2 was 0.35 meters cubed per kilogram. All right. And so the key is it between the V sub F and the V sub G? So V sub F, remember it's already been multiplied by 1,000. It's 0.0011274, and your V sub G is your 0.1941. Well, our specific volume is 0.35. So since our V2 is greater than the V sub G, then I know that it's going to be superheated. So in an outer room, but superheated. Okay. So let's go to our superheated tables. And now normally I know the pressure, right? And so I go to the block according to the block for whatever pressure I'm at. I don't know what the pressure is. And so I'm going to have to interpolate. But I still have two independent intensive properties. So I know that I can fix my state. So let's go 180. All right. So I'm going to start over here. All right. And I'm going to be looking at 180. Okay. So I know that that's not on here, but can I make this a little bit? Maybe I need to interpolate, but probably not. Okay. Kind of clean this up just a little bit. All right. Oh, I just happened to come across it. That was quite convenient. Okay. So again, my temperature 180 and V2 0.35 meters cubed per kilogram. So what I need to do, I'm going to need to interpolate. And so what I'm going to do is I'm going to look along the lines according to 180, and I'm going to start looking for values that are kind of close to 0.35. And I'm going to try to find the place where I have a value right below and right above, and then I'm going to interpolate. So right below 0.35 and right above 0.35. And it looks like I've got it, right? So at 180 and a pressure of 5 bar, so 180 degrees and a pressure of 5 bar, I've got my specific volume of that water would be 0.4045. And at 7 bar and 180, I would have a pressure of I would have a specific volume of 0.2847. So what I'm going to do is I'm going to set up my own little table. I'm going to say, okay, if the temperature was 180, and I'm going to have a little column for specific volume, I'm going to have a little column for pressure, because that's what I'm supposed to find. I figured out it was superheated, right? So now I got to find the pressure. Okay. So, all right. So I'm going to use this guy right here, this guy right here. So if the pressure were 5 bar at 180 degrees Celsius, my specific volume would be 0.4045. If my pressure was 7 bar, then my specific volume would be 0.2847. But I am at 180 degrees Celsius and 0.35 bar. And so I need to interpolate between those values. If you need a little help on, remember, if you need some practice interpolating, there is a video. I can't, you know what? I don't know, but it's on the Unit 1 playlist, and it's called interpolation. So make sure you check that out. But I end up getting a value of 5.91. And you know that you've done it right when you have a value right below or right in between these two values right there. So actually, let's make sure we got this. Sometimes what I see, so the way that you're supposed to do it is you're supposed to work from the same, either bottom up or top down, and just be consistent. So I will always work from the bottom up, meaning that I'll do like this. So this was my P2. So say I didn't know my P2 yet. So I would do, okay, so working from the bottom up, 7 minus 5, right? So I'm looking at this row minus this row. 7 minus 5 over 0.2847. 0.47 minus 0.4045. And then I would say, okay, and then work them from the bottom up. This one minus this one. So I would say that's equal to P2 minus 5 over 0.35 minus 0.4045. And I would solve for P2 that way. What I sometimes see people getting in trouble with, if you get a wrong answer, or an answer where your pressure that you interpolated for, let's say you got like 9 or something like that, but it's, it's not between 5 and 7. What you have probably done is you've probably, instead of consistently going from the bottom to the top, or from the top to the bottom, whatever your preference, as long as it's consistent, you've messed that order up. So for example, you said, I'm going to put it in red. You said 7 minus 5. Okay, perfect. Minus 0.2847 minus 0.4045 equals 5 minus, see now I'm going from the top to the bottom, 5 minus P2 over 0.4045 minus 0.35, right? That's going to get you something that's outside that range of 5 and 7 for P2. So just be aware of that. Always be consistent. Go to from the bottom to the top, or top to the bottom, whatever you do, just be consistent. All right, but anyway, so I found my pressure. Perfect. Right. So we had to interpolate. It's superheated. And I know that my pressure is 5.91. Perfect. So that's my answer for part B. Part C, I needed a TV diagram. Okay, I'll put this in degrees Celsius, this in terms of specific volume. Okay. And let's go ahead and write a dome here. So yeah, let's go ahead and solve it. So I know state 1, superheated. State 2, superheated. So I need both of those dots to be on the right-hand side. Okay. I also know that it's isothermal, which means T1 and T2 are equal to one another. So it's going to be really easy. There's going to be a 1 dot here. There's going to be 1 dot here. Probably need to make it so that'll work on my, there we go. All right. So let's look at our specific volumes. So my V1, 0.28 and change, and V2, 0.35 meters cubed per kilogram, right? Pay attention, it needs to be units of specific volume. So V1 is the smaller one, so that's going to be this one. There's 2. Okay. So there's a V1. There's V1. There's a V2. All right. So just FYI, if you didn't put this guy on the TV diagram, but you included those units right where you defined what V1 is, and same thing with V2, that's fine. So if you got docked points for that, you're welcome to reach out to me and I'll put those points back on. Same thing with your temperature. As long as those units are defined with your temperature somewhere on your paper, that should be fine. What I don't like seeing is T2 is 180 and then just leaving off the units. Don't do that. Don't get in the habit of that. Okay. So I don't like all these circles now either. Go away. There we go. All right. And then over here, T1, T2, and we know we've defined it somewhere else on our paper that it's 180 degrees, so that's fine. And that would give me full credit. I've shown the process path correctly. I've put a dot for 1 and 2, and I've labeled which one's 1 and which one's 2. And I've labeled or defined somewhere what V1 and V2 are, and T1 and T2. Okay, so now let's get our PV diagram. So this is a little bit less straightforward because we're talking about a constant temperature process, right? And the lines of constant temperature on a PV diagram go like this. That, okay? So anywhere on that line is 180 degrees Celsius. That's fine. You don't actually have to label what that line is, but you need to draw that line to make sure that you draw your process path correctly. All right, so um, I think I want to extend this just a hair bit. So there's my specific volume. Again, as long as you put those units, you've defined them somewhere where you've defined your pressure and your specific volume, this is going to be fine. If you've got docked points, please let me know. I'll take a look at it. All right, so state 1 and state 2, both superheated, so those dots need to be out in that superheated region. Um, there's a dot, there's a dot. V1 was the 0.2847 meters cubed per kilogram. V2, 0.35. So here's state 1, here's state 2. I'm going to draw a process path between them. I also need to label P1 and P2. So P2, I know I could have just put P2 and that would have been fine because I've already labeled this, but that's put it anyway just for completeness. And then state 1, we had figured that it was 7 bar. Not that we had figured, we were given that it was 7 bar. And so all those values make sense, right? P1 is bigger than P2, so like where it's situated on the axis. Um, and yeah, looks pretty good. And of course, V1, I'm going to actually write it just so it's obvious, right? This guy's 0.35. So it's always a good idea, even if you just write V1 and V2, just be cognizant of what those values are to make sure that your graph makes sense. All right. Make sure to check out the solution online. There's a rubric about how many points things are worth. If you grade yourself and it's not the same as what the grader put, and you disagree with that, right? That your grade was not what the rubric said it should be, please do reach out to me. I am more than happy to look over that. So, all right, let me know if you have any questions. Thank you.